Hello and welcome to this lecture. So now this notion of diagonalizability and uh, expressed in terms of eigenvalues and all that gives you a lot of ideas and powerful ways to think of these things. So now we are going to see a few of those very crucial nice properties. Okay. First property is eigenvalues and determinant do not depend on the matrix representation, rather they are properties of the operator T themselves. Whatever basis you may pick and whatever matrix you may get for T, the eigenvalues and determinant that you computed will remain the same. Okay, so it seems like a surprising result because it seems to depend on the matrix representation, no? Supposing you have a matrix A with respect to canonical basis, how do you go about finding eigenvalues? They are roots of determinant A minus lambda I. It seems like if A changes, then this polynomial changes, so the root should also change, no? But it turns out the similarity transformation is a special case, right? Because when you go to a new basis, the matrix is not any general change, it is S inverse AS. It has a very special form. So eigenvalues now become roots of determinant S inverse AS minus lambda I equals 0. Okay. Now it turns out these two polynomials are actually the same. Okay. You may be surprised. So you may ask the question, are these two different? So it turns out they are exactly the same. They are no. No is the answer here. Now, how do you get that answer? Here is what you do. This S inverse AS minus lambda I, you pull out the S inverse on this side, S on that side, can be written as S inverse A minus lambda I then S. Okay, notice how easily this came about. Okay, that's because you multiply this through, you will get S inverse AS minus lambda I here, because that will become just S inverse S, that's again I. Okay, so now you can take determinant on both sides. So determinant S inverse AS minus lambda I is determinant of S inverse times determinant of A minus lambda I times determinant of S. Okay, you see that because determinant AB is determinant A into determinant B. So it's a product property, no? So determinant goes into the product. So S inverse determinant A minus lambda I determinant S. Now what else do I know? This is the same as determinant A minus lambda I, because determinant S inverse is 1 by determinant S, right? So 1 equals determinant I equals determinant A inverse determinant A into determinant A inverse. So determinant A inverse times determinant A equals 1. So this goes away. So this guy, determinant of S inverse AS minus lambda I is exactly equal to determinant A minus lambda I. So even though you change the matrix, go to something else by similarity transform, the polynomial equation remains the same. So these two are not different. The eigenvalue becomes an operator property. So eigenvalue of the operator, people also loosely say it's matrix, but remember it's eigenvalues of the operator. Same thing with determinant. Determinant is also an operator property, because determinant, even if you change the basis, if you look at S inverse AS, the same as determinant A, right? Because determinant S inverse into determinant A into determinant S, S inverse and S sort of cancel and you get just determinant A. So it's best to say eigenvalues of the operator, determinant of the operator. Okay, the matrix is, if you do a similarity transform, determinant doesn't change, eigenvalues do not change. Okay, powerful property. There is yet another very important idea in this whole thing, which is upper triangularization. So far we have been talking about diagonalization, and we found this unfortunate result that some matrices are diagonalizable, some are not diagonalizable. We found many examples where it was not diagonalizable. It turns out, however, any operator, whatever the operator may be, all operators, there is some basis for which the matrix is upper triangular. You can't quite get diagonal, something on the upper triangle also will be non-zero. Okay, so as long as you are willing to live with the upper triangular part, then you are okay. Now, upper triangular is not too bad, right? It's mostly, almost like half the elements are gone, so it's somewhat easier. Okay, so for any operator T, there is a basis with respect to which the matrix of T is upper triangular. It's not true for diagonal, right? For every operator, it's not true that there is some basis for which it is diagonal. The matrix is diagonal. It's not true, but for any operator, there is some basis for which the matrix is upper triangular. Okay, the proof I'll only sketch. The proof in detail is a bit of an abstract work, so we'll skip it. We'll not skip it. We'll just give you a sketch of the proof. T has definitely one eigenvector v1 with eigenvalue lambda 1, right? So you pick a basis which is v1, and then you extend v1 to find a basis for fn, right? You do that, and then in this basis, the matrix of T will be lambda 1 0, because the first coefficient is just lambda 1 followed by a bunch of zeros, and then the remaining one will be whatever, I don't know what the stars are. So the idea is, now I've gotten my first column right, sort of I need to pivot into the second column and all that. All of that is actually possible. So, you can proceed with this n minus 1 by n minus 1 matrix in a very similar manner, find its eigenvalues. You can always find a basis where all these things are respected, etc. This may change as you change this, but this lambda 1 won't change. Okay. So, you can have lambda 1, proceed like this ultimately till you get lambda 1, lambda 2, so on till lambda. Okay. So, I know it is not a proper proof, but this sort of method works. Hopefully, you see how this can be made to work. Okay. So, the crucial point is, when you do this in this basis, the numbers that show up on the diagonal are the eigenvalues. So, we have seen that before, right? Now, if you have an upper triangular matrix, determinant is simply product of these diagonal elements. So, if you do the upper triangular matrix minus lambda and then you do determinant, it is just be the triangle elements, right? This minus lambda into this minus lambda, only that will survive. So, the eigenvalues are the values that show up on the diagonal. So, that is what is beautiful about the upper triangular matrix representation. The values you see on the diagonal are actually the eigenvalues. Now, let us go back and look at our geometric and algebraic multiplicity. In fact, there was a relationship between them which we could not prove. No? Once you know the upper triangularization, you can prove it. So, you take an operator T, you consider the basis in which m of T is upper triangular. So, it has got lambda 1, lambda 2, lambda n on the diagonal. Up, I do not know what it has, some stars are there. Below, it is always 0, right. Now, here is the crucial thing. The algebraic multiplicity of lambda is number of times lambda appears on the diagonal, right. If algebraic multiplicity is 1, your lambda will appear only once on the diagonal. If it is 2, it will appear twice, etc. Okay. Now, what is geometric multiplicity? It is dimension of null of m of t minus lambda I, right. So, I have to subtract lambda, the corresponding lambda that I have here on the diagonal, right. Remember, the lambdas themselves occur on the diagonal. How many times? Algebraic multiplicity number of times. Okay. So, m of t minus lambda I has algebraic mul of lambda zeros on the diagonal, exactly, right. How many times lambda appears, that many zeros will be there on the diagonal. What will be the other entries? They will all be non-zero. So, n minus algebraic multiplicity of lambda will definitely be non-zero on the diagonal. Okay. So, that means rank of m of t minus lambda I is at least greater than or equal to n minus algebraic multiplicity of lambda. That many are non-zero on the diagonal. Okay. So, it is greater than or equal to that many. Okay. I do not know about the off diagonals, no. So, the diagonals alone 0, depends on the off diagonal elements, but it has to be at least number of non-zero values on the diagonal, which means by the rank nullity theorem, geometric multiplicity, which is the nullity of m of t minus lambda I, is less than or equal to n minus this guy, which is algebraic multiplicity, because rank and nullity have to add up to n. So, if rank is greater than or equal to this, nullity will be less than or equal to algebraic multiplicity. So, this helps us prove this result we had. The geometric multiplicity is less than or equal to algebraic multiplicity. Okay. So, very nice. This upper triangularization has these nice kind of powerful properties which you can use to prove. Okay. Another property you can prove using this upper triangularizability is sum and product of eigenvalues. So, normally when you saw the matrix, even for a 3 by 3 matrix, when you write down the polynomial, it is a complicated polynomial involving a lot of the values and all that, right. So, it is not clear what the sum of the eigenvalues are, a product of the eigenvalues are. Okay. So, sometimes it may not be clear to you, but it turns out here is a nice result from the upper triangular structure. So, you have an operator T, you consider a basis in which m of t is upper triangular. So, you have got lambda 1 to lambda n on the diagonal, stars on the right top, zeros below. What is determinant of t? It is the same as determinant of m of t, right. I can pick any basis, determinant is the same. But what is determinant here? It is upper triangular, so product of the values on the diagonal, lambda 1 to lambda n. So, product of eigenvalues. What is on the diagonal? Eigenvalues. So, product of eigenvalues is always determinant of the operator. Wonderful result, isn't it? Determinant of the operator is product of the eigenvalues. Nice result. Now, to go towards the sum, we need to define something called trace. What is trace of a matrix? Trace of a matrix, sum of its diagonal elements. Okay, add up all the elements on the diagonal, it is called the trace of the matrix. So, here is a very easy property you can show. If A and B are n cross n matrices, trace AB is trace BA. Okay, just algebraically you can show all the diagonal elements will match both on AB and BA. So, trace AB will be trace BA. Okay. So, trace is actually an operator property, it is not a matrix property. If you do a similarity transform, right, trace of S inverse AS, now AB is BA, right. So, you define this as your A and then this S alone as your B. So I can bring this S to this side, trace doesn't change. So S into S inverse A, but SS inverse I. So it becomes a trace of I. So if you do a similarity transform, trace does not change. Okay, so trace is an operator property. You have an operator, you find a matrix with any basis, you sum up the diagonal elements, you will get one value, right? You do S inverse AS, go to any other matrix for any other basis, sum of the diagonal elements will remain the same. Just like determinant remains the same, so trace is also an operator property. Now, once you know that, it's very easy to see trace of T is a trace of M of T, which is sum of the diagonal elements, which is lambda 1 plus lambda n, which in fact for M of T is the sum of the eigenvalues. Now, eigenvalues are also operator property. So, sum of eigenvalues is trace of T, trace of the matrix M.